Tree representation using linked list. In the previous lecture, we learned how to represent tree using arrays. And in this lecture, we are going to see how to do the same using linked list. So coming to arrays, we had seen that there is this problem that space will get wasted if we are representing a tree which is not a complete binary tree, right? That is with the most common representation that we used in array. Coming to linked list, we'll resolve this problem. Here, you can represent any sort of tree without wasting space. So we'll first go to the most common representation that we use, which is pointer node representation. Here, each node will contain data and reference to its children. So let us say this is a node. It will have data, let us say 30, and it will have references to children. So normally in a linked list, each node in a linked list will have a pointer which point to the next node. That will again point to the next node. In a similar way, in tree, each node will point to its children. So if this is having two children, left child and the right child, it will have two pointers which will point to one to the left child and the second to the right child. This again will have data. And again, if it is also having children, there will be more pointers coming out of these. This representation is mostly used in order to represent binary trees. And the main advantage is, in case of arrays, we had discussed that if this 30 is not having right child, then space will be wasted in the array. Because in array, if you are not having this child at all, in that case, you will still have to leave the space because this space is supposed to be for right child of 30. Coming to linked list, if there is no right child, just don't add that link. It's as simple as that. So linked list is more flexible. Moreover, this is intuitive. That is, you have a root on top, then you have pointers to the children. That child again have pointer to the child of that. So this is more intuitive approach as well. And especially in recursive approaches, this works very well. So this is about the most common representation of linked list that is used. There is one more representation that you should know, which is not very commonly used, but it is useful in certain cases. It is called left child right sibling representation. So in this representation, what we do is, so this is designed more for all sort of general trees, and the previous one that we discussed, that is mainly for binary trees. You can use any sort of trees, but the problem is you will have to define a structure. So in that structure, you will have to define that each node will have data, then a left pointer and a right pointer. So if you want to have more pointers instead of this left pointer and right pointer, you will have to define some list array or something. In left child right sibling representation, it doesn't matter whatever be the number of children, you can use for any sort of generic trees. So in left child right sibling representation, it goes like this. If this is a node, this is 30. It will not have links to all its children, but only left child. That is why it is called left child right sibling. So in left child, 30 will have a link to the leftmost child of 30. So if this is 20, you won't have this link to the right child. Instead, this child will have a link to the sibling. So if this is the sibling, this is actually right child of 30. But instead of this link, you are having the link from sibling. And the advantage of this representation is, this sibling can again have link to the next sibling. This sibling can again have link to the next sibling. So even if there are a lot of children for the same node, it's easily representable through left child right sibling representation. If 10 is again having children, so there will be again a link from 10. And if this child is having siblings, to the sibling there will be a link. So on each node, there will only be maximum two links. One link to the left child, one link to the right sibling. So here 20 is a node. 20 doesn't have children, so there is no link for left child. But it has a right sibling. So there is a link for right sibling. But in case of 10 has both a sibling as well as a child. So this is how left child right sibling representation work. So what this does is, this reduces the need of multiple child pointers. This is the advantage. And secondly, it is easily navigable between the siblings. If it is a previous representation, if each parent you had representation linked towards children, navigation between siblings is not easy. You have to go to the parent and then come back to siblings. But in left child right sibling representation, navigating through the siblings is easier. But traversal might be complex because this representation, the common representation that is used, that is easier for traversal. So we'll go to tree traversal techniques, though it will be clear for you why it is useful for traversal and what sort of tree traversal techniques exist.